Welcome back to the deep dive. You know, I was reading through this massive stack of reports you sent over. The space situational awareness assessments, the planetary defense protocols from NASA, ESA, the works, and I had this distinct moment where I looked out the window.
Mm-hmm.
It was a nice day, sun was shining, birds were chirping, and I felt deeply, profoundly unsettled.
That is a very, very common reaction when you actually look at the data rather than just, looking up at the pretty blue sky. The data tells a very different story than our eyes do.
It's the dissonance, right? We
Yeah.
go about our lives, we commute, we grab coffee, we worry about our emails or the stock market, and we're completely ignoring the fact that Earth is currently hurtling at 67,000 miles per hour through it's essentially a cosmic construction site.
Yeah.
It's a messy construction site. There's debris everywhere.
Construction site is actually a better analogy than the usual shooting gallery. Because, this isn't random fire from an enemy, it's leftover material.
Left over from what?
What we're talking about today are the scraps from the formation of the solar system. The brick and mortar that didn't quite make it into the planets. And the reports, they make it crystal clear. We are being hit constantly.
Constantly.
I'm talking about 100 tons of dust and sand-sized particles hitting Earth's atmosphere every single day.
100 tons. That's a blue whale's worth of space dust falling on us every 24 hours. But, we aren't here to talk about the dust.
No?
That stuff just burns up and makes pretty shooting stars. We're here to talk about the city killers, the
Yeah.
planet killers.
The near-Earth objects, or NEOs.
Mm-hmm.
The rocks that are big enough to survive the atmosphere and punch a hole in the ground.
Exactly. So the mission for today's deep dive is to perform an audit, essentially,
Mm-hmm.
on the global security system that is supposed to be watching these things. I want to know who is manning the radar, how the technology actually works, beyond just taking a picture. And I really, really want to dig into the blind spots. Because as I read through the capabilities of the US, China, Russia, and especially that section on India, it became clear that there are some massive holes in the fence.
There are. And as we discuss these reports, you'll see that while the technology is incredible, we are doing things today that were just science fiction 20 years ago. The geopolitics are messy.
Messy how?
We have a fragmented shield. It's not the unified Earth Defense Force you see in the movies, not by a long shot.
So let's start with the basics then, the toolkit. If I'm an astronomer and my job is to save the world, what is actually in my utility belt? How do we see a rock that's millions of miles away, moving at thousands of miles an hour against a backdrop of billions of stars?
It is not easy. It's incredibly difficult. Basically, humanity relies on a triad of technology. You can think of them as the eyes, the speed guns, and the night vision.
Okay, let's start with the eyes. I'm guessing these are the optical telescopes, right? This seems straightforward. You look up, you see a rock.
It seems straightforward, but the mechanics of discovery are actually quite, tedious. You don't just see an asteroid in a single glance.
Why not? It's a big moving thing.
Because stars are fixed points of light. They are so far away that for all intents and purposes, they never move relative to each other. Asteroids, on the other hand, are much, much closer, so they appear to move against that fixed background.
So it's a game of spot the difference.
Exactly. It's a process called astrometry. The big surveys, like Pan-STARRS in Hawaii or the Catalina Sky Survey, they take a photo of a patch of sky.
Okay.
Then, maybe 15 minutes later, they take another photo of the exact same patch, then another. Then they stack them, and a computer algorithm sifts through the data.
Looking for what?
The computer looks for the one dot that has shifted its position while all the other billions of dots stayed perfectly still.
So it's like a flipbook animation.
Precisely. That's a perfect analogy. If it moves, it's a rock in our solar system. If it stays still, it's a star far, far away. But, optical telescopes have a massive limitation, a fundamental flaw that physics just imposes on us.
They need the dark.
Right. You can only see at night. But there's a more critical issue. You cannot look close to the sun.
The glare would be too much.
It's totally overwhelming. It would fry the sensors. So if an object is coming from the direction of the sun, from the daylight side of Earth, our optical telescopes are completely blind to it.
Which, I have to say, feels like a pretty big design flaw in our planetary defense system, considering the sun is, blocking half the sky at any given moment.
It is the single biggest blind spot.
Okay, but we'll get to the scary implications of that in a bit. Let's talk about the second tool, the speed guns. This is planetary radar.
Yes. And if optical telescopes are the scouts that find the threat, radar is the intelligence unit that characterizes it. It's the heavy lifter when it comes to precision.
So optical finds the fuzzy dot.
It tells us, hey, there is a fuzzy dot at these coordinates. But an optical telescope, especially at first, is terrible at telling you exactly how far away it is, or, more importantly, where it's going in 3D space. That's where radar comes in.
And this is just bouncing radio waves off the rock.
Yes. But we need to be clear about the scale here. When we say radar, most people think of the skinning dish at an airport tracking a 747 a few miles away.
Right.
Planetary radar is infinitely more powerful. We are talking about beaming a focused radio signal, sometimes with the power of a small city, millions of miles into the void, trying to hit a rock that might be only a few hundred meters wide, and then trying to catch the echo.
The signal loss on that must be insane.
It is. It's governed by the inverse square law, but it's applied twice. You lose power on the way out as the beam spreads, and you lose power on the way back as the faint echo spreads.
So what comes back is tiny.
The signal that returns to Earth is often less than a billionth of a watt. It is a whisper at the quantum limit. It's barely there.
So how do we get any useful data from a whisper? I mean, how does that tell us if the rock is shaped like a sphere or a rubber duck?
We use a technique called delayed Doppler imaging. It's just brilliant physics. We measure two things with incredible precision. First, the time it takes for the signal to bounce back. That's the delay.
And that gives you the distance.
Exactly. Down to the meter from millions of miles away. Second, we measure the Doppler shift.
Like the sound of an ambulance siren changing pitch as it drives past you.
It's the exact same principle. If the asteroid is spinning, one side of it is rotating toward us and the other side is rotating away.
Okay.
The side moving toward us squishes the radio waves, shifting the frequency up. That's a higher pitch. The side moving away stretches them, shifting the frequency down a lower pitch.
Ah, I see.
By mapping all these tiny frequency shifts across all the delay times, we can actually reconstruct a 3D model of the asteroid's shape.
That is wild. So you're essentially hearing the shape of the rock based on how it changes the radio pitch.
Precisely. And that shape data is vital. I mean, if we ever have to deflect one of these things, we need to know if we're hitting a solid iron boulder or just a loose pile of gravel held together by weak gravity. Radar is what tells us that.
But radar has a range limit, doesn't it? You can't just scan the whole sky with it.
No, absolutely not. It's a spotlight, not a floodlight. You have to know where to point it first. The workflow is almost always optical telescopes find the target, and then we use radar to characterize it.
Which brings us to the third tool, the night vision. The source material mentioned infrared. Why do we need that if we have optical telescopes?
Because space is dark, and not all rocks are shiny. In fact, some of the most dangerous asteroids are incredibly, incredibly dark. We call them carbonaceous asteroids because they're rich in carbon.
So they're like giant lumps of coal floating in space.
That's a great way to think about it. Now imagine a piece of charcoal flying through a coal cellar at midnight. That's what we're looking for.
Hard to see.
Very hard. An optical telescope relies on reflected sunlight. If the rock only reflects 3% or 4% of the light that hits it, which is the albedo of charcoal, it is almost invisible against the blackness of space until it is right on top of us.
So optical fails in that case.
Optical fails. But even if a rock is pitch black, it still absorbs sunlight. And if it absorbs sunlight, it gets warm. And anything that's warm re-radiates that energy as heat.
And that's what infrared sees, heat signatures.
Exactly. To an infrared telescope, that dark, stealthy rock glows like a beacon against the cold background of deep space. It turns the stealth bomber into a flare.
So why don't we just use infrared all the time?
The catch is you generally have to put these telescopes in space. Earth's atmosphere, all the water vapor in it, blocks a lot of infrared light. That makes it expensive.
So we have eyes, speed guns, and night vision. On paper, it sounds like a pretty solid setup, but then I looked at where these tools are actually located on the globe, and there seems to be a geography problem.
The northern bias, absolutely. Historically, the vast majority of the world's wealth, and with it, its scientific infrastructure, has been in the northern hemisphere, the US, Europe, Russia, China. So naturally, that is where they built the big telescopes and the powerful radars.
Which means we have been watching the northern sky very, very closely, and the southern sky, not so much.
For a long time, it has been a back door, a huge blind spot. If an asteroid approached Earth from a southern trajectory, say, coming up from below the plane of the solar system towards Antarctica, The major assets in the US or Europe simply physically could not see it because the Earth itself was in the way.
That's why the southern observatories are so important.
This is why countries like Australia, South Africa, and Chile have become so critical to planetary defense. They are the guardians of the southern sky.
Okay, so we have the tools, and we are at least trying to cover the whole map. But let's get into the oops files, because nothing makes this more real than the times the system failed. And the headliner here, I mean, it has to be Chelyabinsk.
February 15th, 2013. A cold morning in Russia. This is the event that really changed planetary defense from a niche academic interest into a global security priority.
Walk us through the timeline. Because this wasn't 1908, this wasn't Tunguska. We had satellites, we had radar, we had the internet. How did a 20-meter rock sneak up on us?
It is entirely about its trajectory and that solar blind spot we mentioned just a minute ago. The Chelyabinsk impactor was coming from the direction of the sun.
Hidden in the glare.
Perfectly hidden. In the sky, from our point of view, it was visually very, very close to the sun.
Our best optical telescopes couldn't even look there.
They would fry their sensors. So this rock is approaching at roughly 40,000 miles per hour, hidden entirely in the solar glare. It hits the atmosphere. Now, usually small rocks burn up, but this one was about 12,000 tons of stone. It was the size of a 6-story building.
So it didn't just burn up.
No, it punched through the upper atmosphere and only detonated when the atmospheric pressure became too great for it to hold together. That happened about 30 kilometers up.
And the explosion. I've seen the dash cam footage. Everyone has. It looked brighter than the sun for a second.
It was. It released about 500 kilotons of energy. To put that in perspective, that is roughly 30 Hiroshima bombs. But here's the really scary part, and the part that I think most people don't understand about asteroid impacts. The damage didn't come from the impact itself.
It didn't hit the ground.
It didn't slam into the ground and make a crater. No, it exploded in the air.
Right, so what hurt everyone if it didn't hit anything?
The shock wave. It's a simple physics problem. Light travels faster than sound. People saw this massive, silent flash, a second sun streaking across the sky. And naturally, what do you do when you see something like that?
You walk to the window to look.
Of course you do. Everyone did. But the shock wave was lagging behind. A minute or two later, that wall of compressed air slammed into the city of Chelyabinsk.
And the windows.
It blew out windows in thousands of buildings across the city. Over 1,500 people were injured, mostly by flying shards of glass.
That is such a chilling detail. Their own curiosity is what hurt them.
And think about this. If that rock had been just a little bigger, say 50 meters wide instead of 20, it wouldn't have just broken windows. It would have leveled the buildings. And the key takeaway from the reports is this. We had zero warning, not days, not minutes, not seconds. The first warning anyone had was the flash in the sky.
Zero. And it's not just the ones we miss completely, right? It's the ones we see at the very last second. I was looking at the data on this one. 2019 OK.
Ah, yes. The city killer. That one was a real wake-up call.
That's a comforting nickname.
Well, it was about 100 meters wide, so if that hits a populated area, it destroys a metropolitan area completely. In 2019, it passed within 70,000 kilometers of Earth.
70,000. That's less than 1/5 the distance to the moon.
It was an uncomfortably close shave, a cosmic near miss.
And when did our global security systems spot this one?
One day before its closest approach.
One day. So if it had been on a collision course, we would have had 24 hours to, well, panic, mostly. That's about it.
Exactly. There is no deflection mission you can launch in 24 hours. You can barely organize an evacuation of a single city in that time. And then there was 2023b, just recently.
What about that one?
A smaller object, maybe the size of a delivery truck, but it passed just 3,600 kilometers above the surface of the Earth.
Wait, 3,600? That is closer than our satellites.
It is. We have our big telecommunications satellites orbiting at 36,000 kilometers in geostationary orbit. This rock undercut them by a factor of 10. It passed between us and our own satellite.
And the warning time.
Detected only days prior. It really highlights that while we are looking, we aren't seeing everything. Not even close.
It really does. But we have to talk about the big one. The one that actually genuinely scared the experts. Apophis.
Apophis is legendary. It's a legend in the planetary defense community. It was discovered back in 2004. It's a big asteroid, roughly 340 meters across.
And that's big enough to do what?
That's big enough to cause continental scale devastation. An ocean impact would create tsunamis that would wipe out coastlines. A land impact would be a global catastrophe. So when they first found it and ran the math on its orbit, the initial calculations were Alarming.
Alarming is a very polite word for it. The source material says they calculated a 2.7% chance of it hitting Earth in 2029.
Which is just a terrifyingly high number in this field. Usually we talk about probabilities like 1 in a million or 1 in 10 million. A 2.7% chance is roughly 1 in 37.
If I told you there was a 1 in 37 chance your plane would crash, you wouldn't get on it.
I absolutely would not. It caused genuine fear at NASA and around the world. There was this concept they were worried about called the gravitational keyhole.
The what?
The fear was that even if it missed us in 2029, its trajectory might pass through this tiny region of space, a keyhole, where Earth's gravity would tweak its orbit just enough to guarantee it would hit us on the next pass in 2036.
So how did we resolve it? Why aren't we all building bunkers right now?
Radar. This is where the speed guns saved the day. As they got more and more radar observations over the next few months and years, they refined the orbit. They were able to rule out the 2029 impact and then eventually the 2036 keyhole.
So it's going to miss.
It will miss. It's going to pass very close in 2029, about 31,000 kilometers away, so close it will be visible to the naked eye, but it will miss us.
So Apophis became a symbol of how uncertain this tracking game can be. It starts with abject terror and ends with more math.
But the math is only as good as the data. And the statistical reality, the thing that keeps me up at night, is what the data says we don't know.
Which is?
The sources indicate that for asteroids larger than 140 meters, those are the ones that can end a country or a civilization, we have found maybe 40 to 50% of them.
Hold on. So half of the country killers are still completely undiscovered, just floating out there, their orbits unknown.
Correct. And for the smaller ones, the city killers, like the one that caused Shelly Bins, we have found maybe 1 to 5%.
1 to 5%.
We are effectively playing a cosmic game of dodgeball, blindfolded, in a gymnasium the size of the solar system. For every close call we track, there are likely several we never saw at all.
Okay, so who is actually watching the gym? Let's get into the geopolitics of this, because while space is for everyone, the radar dishes and the telescopes definitely belong to specific countries. Who is the heavyweight champion here?
Historically and currently, it is the United States, without a doubt. NASA funds roughly 90% of all near-Earth object discoveries globally.
90%.
Yes. So if you see a headline about a new asteroid being discovered, the odds are extremely high that it was found by a U.S.-funded program.
And what are the big assets? What's in their toolbox?
They have the Goldstone Solar System radar in California, which is the heavy lifter for tracking and characterization. They run the Catalina Sky Survey and Pan-STARRS, which are the primary hunters scanning the sky every single night. And they have the Space Fence in the Marshall Islands, which is this massive radar system, primarily for tracking satellites and debris, but it contributes.
But the U.S. took a big hit recently, didn't it? In terms of its capabilities.
The collapse of the Arecibo Observatory in Puerto Rico in 2020, that was a tragedy for science, and frankly, it was heartbreaking to watch. I'm sure you saw the video of the cables snapping and the 900-ton instrument platform just crashing down into the dish.
Yeah, it looked like a scene from a disaster movie, just
yeah.
Catastrophic failure.
It was the most powerful planetary radar in the world. It was the best tool we had for getting high-resolution images of these rocks. Goldstone is great, but Arecibo was the king. Losing it left a significant gap in our capabilities. We lost our best magnifying glass.
So the U.S. is leading but stumbling a bit. Who is coming up behind them? Who's the contender?
China is the rising power, unquestionably. Their expansion in space situational awareness is rapid. They have the FAST telescope, the 500-meter aperture spherical telescope.
That's the huge one built into a valley, right?
The very same. It is the world's largest radio telescope now. And they have built new, powerful deep space radars in places like Xinjiang.
And they have plans for their own dedicated asteroid hunters.
Yes. They've announced plans for a whole constellation of asteroid hunting satellites set to launch between 2025 and 2030. They realize that relying on U.S. data is a strategic vulnerability. They want their own eyes on the sky.
What about the old guard, Russia?
Russia is interesting. They have incredible capability, but their focus is very different. Their radar network, the Voronezh systems, is one of the densest in the world, but it is primarily designed for missile warning.
So they are watching for nukes, not rocks.
They watch for rocks too, of course, especially after Chelyabinsk. But the data is often classified or at least military-focused. They participate in global discussions, but they don't share discovery data as openly or as prolifically as the U.S. surveys do. It's a different philosophy.
And Europe, what's their role in all this?
The European Space Agency, ESA, plays the role of the coordinator. They have the Near-Earth Object Coordination Center, the NEOCC in Italy. They're also very focused on developing specific technologies. They're building the FlyEye telescope.
The FlyEye.
Yeah, it's a cool concept. It splits the image into multiple channels to cover a wider field of view, kind of like a fly's compound eye. And of course, they are leading the Hera mission, which is the follow-up detective mission to NASA's Dart Deflection Test. They're going back to the scene of the crime to see exactly what happened.
I want to pivot now to a specific region, the source material highlighted, which I think is often overlooked in these big Western-centric discussions. India. The analysis argues that India is uniquely vulnerable to this threat. Why is that?
This is a crucial point that ties back to geography and population density. When we think of asteroid impacts, thanks to Hollywood, we usually think of a rock hitting a city, New York, London, Tokyo, or maybe it hits land and creates a giant dust cloud.
Right, the classic disaster movie scenario.
But the Earth is 70% water. Statistically, any given asteroid is most likely to hit the ocean.
And for India, that is a nightmare scenario.
Look at the map. It's plain to see. India is a massive peninsula jutting out into the Indian Ocean, with the Arabian Sea on one side and the Bay of Bengal on the other. You have 7,500 kilometers of coastline, and that coastline is packed with megacities. Mumbai, Chennai, Kolkata, millions upon millions of people living at or very near sea level.
So if a rock hits the water,
you get a tsunami. But not a normal tsunami, not like one from an earthquake.
How is it different from, say, the 2004 tsunami that was so devastating?
An earthquake tsunami creates a wave by shifting the entire seafloor. It moves a vast column of water from the bottom up. It has a very long wavelength. An asteroid impact is a point source explosion. It punches a hole in the ocean. It literally creates a transient cavity in the water.
A crater in the sea.
Exactly. And when that cavity collapses, when all that water rushes back in to fill the hole, it shoots a massive jet of water upwards and sends out a concentric shock wave of waves. These waves can be incredibly steep and incredibly tall.
How tall are we talking?
If a medium-sized asteroid, say a few hundred meters across, hits the Arabian Sea, it could generate waves 50 to 100 meters high near the impact site.
100 meters. That's a skyscraper made of water.
And unlike an earthquake where you might have hours of warning as the wave travels across the ocean, an asteroid impact sends shock waves traveling at the speed of sound through the water. The warning time for coastal India could be just minutes. The 2004 tsunami killed over 230,000 people. An asteroid impact could be orders of magnitude worse.
So for India, planetary defense isn't just about saving the world in some abstract sense. It's about existential security for its entire coastal population. So what are they doing about it?
Well, India's space agency, ISRO, is world-class, and they are famous for being incredibly, incredibly cost-efficient. I mean, their Mars orbiter mission costs less than the budget of the movie Gravity.
Which is still one of my favorite facts in all of science.
It's amazing. They have a very strong mathematical and computing base, and they have some distinct geographical advantages, specifically the Hanmal Observatory in Ladakh.
That's way up in the Himalayas, right?
Yes. It's one of the highest observatories in the world. The air is thin, it's dry, it's clean. It is perfect for optical tracking. And geographically, it fills a crucial gap between the observatories in Australia and the ones in South Africa.
So it's a vital link in the global chain.
It could be. And it should be. But here is the catch that the reports point out. India's current focus for SSA, that's Space Situational Awareness, is primarily on protecting its own satellites.
So they're worried about space junk.
They're tracking space debris that might hit their valuable assets in orbit. They are not yet fully focused on hunting asteroids, which is planetary defense. It's a subtle but important distinction.
So they're watching the traffic in low Earth orbit, but not the incoming missiles from deep space.
That's a good way to put it. There's a gap there, but the potential is huge. Take the Aditya L1 mission, for example.
That's their solar satellite, isn't it?
Yes, it's designed to study the sun. But where they parked it is what's important. It's at L1 Lagrange point, a stable spot of gravity between the Earth and the sun. That is strategic real estate for planetary defense.
Because it can look back towards Earth and see things coming from the sun.
Exactly. While its sensors are for solar physics, simply having a platform there puts India in the perfect position to help with that sun blind spot we talked about earlier.
So the recommendation from the experts in our source material is pretty clear. India needs to pivot some of that amazing, cost-effective engineering capability towards dedicated NEO tracking.
Precisely. They need their own dedicated telescopes to triangulate data with the West. If a rock is coming over the Indian Ocean, we don't want to have to rely on a telescope in Arizona to spot it at the last minute. We want eyes on the ground in India.
So let's say the system works. Let's be optimistic. The U.S. radar pings it, the Indian telescope confirms it, and we know a rock is coming. What do we actually do? Because spotting the bullet is one thing. Stopping it is a whole other ballgame.
This is where we move from observation to deflection. And the good news, the really good news, is that we have recently moved from theory to practice. We have actually entered the era of planetary engineering.
You're talking about the DART mission.
The Double Asteroid Redirection Test. In 2022, NASA took a spacecraft, it was basically a vending machine-sized probe, and slammed it into an asteroid called Dimorphos at about 14,000 miles an hour.
Now, I have to play devil's advocate here for a second. Dimorphos is a mountain floating in space. DART was a golf cart. How does hitting a mountain with a golf cart actually do anything?
It sounds futile, doesn't it? Like a bug hitting a windshield. But it works because of momentum transfer. And here is the key insight from the report that I think most people missed. The beta factor.
Beta factor, what's that?
When DART hit the asteroid, it didn't just push it, it excavated a huge crater. It blew tons of rock and dust out into space in the opposite direction. That plume of ejecta acted like a rocket engine.
Wow.
The force of all that rock flying backwards pushed the asteroid forwards with even more force.
So the asteroid effectively thrust itself off course after being hit.
Exactly. The ejecta enhanced the push from the impact by a factor of roughly 3 or 4. They hoped to change its orbit around its parent asteroid by about 10 minutes. The final result. They changed it by 33 minutes. It was a resounding success, a total proof of concept that we can move rocks in space.
Okay, so we can nudge them. That's fantastic news. But what if the rock is huge? Or we don't have years of warning time for a small nudge to be enough? That's when people start talking about the nuclear option.
Yes, but we need to clear up a massive, massive misconception here. In movies like Armageddon, they land on the asteroid, they drill a hole, they drop a nuke in, and they blow it into a million pieces.
Right.
That is the worst possible thing you could do.
Why? Blowing it up sounds pretty effective.
Because then instead of one big rock hitting Earth, you have a shotgun blast of radioactive rocks hitting Earth. You haven't solved the problem, you've just multiplied it. And now the impact zone isn't just one city, it's half a hemisphere.
Okay, so no drilling. How do we use the nuke then?
You use a technique called standoff detonation. You fly the nuke to the asteroid, but you don't touch it. You detonate it a few hundred meters away from the surface.
A near miss, on purpose.
A very carefully calculated miss. The nuclear explosion releases a massive, instantaneous burst of X-rays and neutrons. These hit the surface of the asteroid and instantly, violently vaporize a thin layer of rock.
It basically burns the skin off one side of the asteroid.
Violently, yes. That vaporized rock expands explosively away from the surface. It creates a powerful jet of gas. And according to Newton's third law, that jet pushes the asteroid in the opposite direction. It's like turning the asteroid itself into a rocket engine for a split second.
That is incredibly cool and also incredibly terrifying.
It is the break glass in case of emergency option. It packs the most punch if you're short on time or if the rock is truly massive.
And then there is the third option, which sounds much more civilized, the gravity tractor.
This is the gentle method, the elegant solution.
Yeah.
This is for when you have years, or preferably decades, of warning. You don't touch the asteroid at all. You fly a heavy spacecraft right next to it, and you hover there.
And gravity does the rest.
Every object in the universe has gravity, even a spacecraft. The spacecraft pulls on the asteroid, and the asteroid pulls on the spacecraft. By constantly using its thrusters to maintain its position and not fall into the asteroid, the spacecraft acts as a tow truck, slowly, imperceptibly, tugging the asteroid off its collision course over a period of many years.
It's the long game.
It is elegant, it's precise, and it's safe. But it requires time. And time is a luxury we might not have if we don't fix our detection blind spots.
Which brings us to the final section of our deep dives today, the dream versus the reality. We know what we can do. We know what we should do. But what is actually happening? What's the state of play?
The ideal global system is clear. All the experts in the reports agree on what it should look like. You want 4 distinct layers of defense.
Okay, what's layer 1?
Layer 1, deep space infrared sensors, probably in orbit, designed to find threats 5 to 10 years out. That's your early warning.
Layer 2.
Layer 2, a global radar grid that can hand off tracking from a station in China to one in India to one in Europe to one in the US seamlessly as the Earth rotates.
So continuous, 247 tracking.
Yes. Layer 3, Rapid response systems on the ground, like the ATLAS survey, which are designed to spot the smaller, closer things with only days or weeks of warning. And Layer 4, a deflection fleet, rockets on the launch pad, ready to go.
That sounds great. It sounds like something we should have, so why don't we have it?
3 things: politics, money, and authority.
Let's unpack politics first. That seems like the biggest hurdle.
Space surveillance is a classic dual-use technology. A powerful radar that can track a small asteroid from millions of miles away can also track a spy satellite or a ballistic missile with incredible precision.
And countries don't like sharing that kind of information.
Exactly. The US, China, and Russia are all deeply suspicious of each other's capabilities. Sharing high-fidelity radar data is hard when geopolitical relations are tense. You don't want to show your adversary exactly how good your eyes are.
Okay, so that's politics. What about money? I assume building this 4-layered shield is expensive.
Actually, and this is a really tragic part, it is shockingly cheap in the grand scheme of things. NASA's entire planetary defense budget is roughly $360 million a year.
$360 million. I mean, that sounds like a lot to a normal person, but in government terms.
To put that in perspective for you, a single B-21 Raider stealth bomber costs about $700 million. We are spending less on protecting the entire planet from a literal extinction event than we spend on half of one bomber.
That is a genuinely depressing statistic.
It is. And then there's the third problem, authority. The who puts their finger on the button problem. If a rock is coming, who decides to launch the nuke?
The UN, the Security Council.
Maybe. But imagine this scenario. A rock is predicted to hit North America. The U.S. wants to deflect it with a kinetic impactor. But the physics of deflection isn't perfect. If the deflection is only partially successful, the new tweaked trajectory might create an impact in Asia.
Oh, wow. So saving New York might mean destroying Mumbai.
Exactly. The geopolitical liability is a nightmare. Who is responsible for that? There is no Earth president. There is no single unified chain of command for planetary defense. If we have to act fast, geopolitical arguments could paralyze us until it is far too late.
However, we don't want to end on total doom and gloom. There is some new hope on the horizon. The reports mention some new tech coming online soon.
There is, and it's genuinely exciting. First, we have the NEO Surveyor. This is a NASA mission launching around 2027. It is that dedicated infrared hunter we talked about. Its whole job is to find those dark, carbonaceous asteroids and the ones hiding near the Earth's orbit.
So we're finally getting some proper night vision in space.
We are. Then there is NEOMIRE. That's an ESA mission planned for around 2030. This one is designed specifically to sit between the Earth and the Sun at that L1 point again and look directly into the glare. Its sole job is to fix the Chelyabinsk blind spot.
So no more surprise attacks coming out of the sun.
That is the goal. And finally, and this is maybe the biggest game changer, on the ground, we have the Vera Rubin Observatory in Chile. It comes online very soon, around 2025.
And what's special about it?
It is a beast. It's an absolute monster of a survey telescope. It will scan the entire visible sky from the southern hemisphere every 3 nights.
The entire sky every 3 nights. That's an insane amount of data.
It is going to create a data revolution. It will find millions of new objects. It will likely find more asteroids in its first year of operation than we have found in all of human history combined.
That is incredible. So we are really moving from being sort of helpless to being aware.
We are. The shield has holes, yes.
Yeah.
Big ones. But we know where they are, and we're finally building the patches to cover them.
So when you boil it all down, what does this all mean for you, for me, for the listener?
It means we are at a unique and I think a very privileged point in human history. For the first time ever, we aren't just dinosaurs waiting for the sky to fall. We have the technology to protect the planet. The physics works. The engineering works. The only missing pieces are political will and funding.
It brings up a provocative thought for me. We spend so much time, energy, and money worrying about borders and economies and conflicts between nations.
We do, and I think I'll leave you with this final thought from the analysis. We invest trillions of dollars every single year in defense against other humans. We build armies, navies, air forces. We invest literal pennies on the dollar by comparison in defense against the universe.
And the universe has a pretty good aim when it wants to.
One day, the universe will test that budget allocation. It will throw a rock at us. The question is, will we have fixed the blind spots before that day comes? Or will we be arguing over who pays for the rocket while the sky turns to fire?
Something to think about the next time you look up at the stars. It's beautiful, but it's busy up there.
It certainly is.
Thanks for listening to this deep dive. We'll catch you on the next one. Stay curious and keep watching the skies.